This one, the one that we saw before is a linear one. Hexane is a linear chain. So whatever, where it breaks, it only make a primary cation or the methyl radical with the methyl cation. But these ones are branched. When you still branch the molecule, it complicates a little bit. So let me show you what each one to produce. If you break this one, and then cations are given this part, you make a primary cation, right? And the methyl radical. And then we already talked about the making methyl radicals is really bad idea. So probably you're not going to see that. These breakages probably not going to happen as much as the other one. The next one, if you break it there, then you're going to make that one like a primary cation. You're going to make that one radical. So it's a primary radical, which is better than the other one because that's a primary cation. So I guess the cation stability is the same, but the radical stabilities are different. The primary radicals are better than the methyl radical. So that breaking that bond is much easier than this one. So you're going to see more of that. But we can continue. What about breaking that one? If you break this one and give a cation this way, that makes secondary cation. Secondary cation is not just twice better than the primary cation, maybe 100 times better than the primary cation. This is a lot more stable than this primary cation. That is a much more preferred compared to that. I mean, it still make a primary radical, but if you're breaking that one, it makes a much better secondary radical. So because of that, what would be the most abundant pick, which is called as a base pick? Remember that? I told you, remember that one thing? Base pick. What's a base pick of that is it should be the most stable cation is going to give you the pick, right? So you're going to think about what would be the most stable fragment you could make with it. And then that would be breaking this one and make a, the secondary cation. That's this one right there. That's a base pick. And then the one, this breaking out that one you see that's not there because these make a primary cation. That even is not possible. So that's why those things are not there. The methyl groups taking off, as I told you about, the methyl radicals are bad. So taking out the methyl groups bad. But why that one showing as bigger than that one, right? Just try to go one more time. This signal, that one, is breaking the ethyl groups. That one taking off ethyl, the molecular weight of the ethyl plus 29. So 29 was taken out because we kicked these ethyl groups out. That's responsible for this one. That's much smaller than once we just take out the methyl groups. But I told you that that's not going to have much happening compared to that one because the methyl radicals are bad. So why this one is showing bigger than 0? Why the methyl groups are coming up more easier than the ethyl groups? It sounds like I'm contradicting what I said earlier, right? But you got to think about this is not the only methyl group in the molecule. Where else the methyl group is there? Can you find it? Can you find a way to kick the methyl groups out? Still make a stable cation. It's not that one. What it is, that one. All the information are hidden in the structures. You have to look at it. You got to imagine what's going to be formed by breaking each part. If that looks like a methyl group, if you only look at it that way, you're not going to solve this problem. So you got to really looking at every angle. That methyl group is taken out, then you're going to make a secondary carbocation. I told you the secondary carbocation is better than the primary carbocation. This is not as good as making the primary radical. So that's why the base pick is not this one. But that way, at least you're making secondary carbocation by kicking the methyl groups out. That methyl group is this one, not that one. That is responsible for that pick. Okay, the structure is what dictates what you get. So anyway, so I know that's not as big as this one. It's all because of, it's a secondary cation, that's secondary cation, but the radical stability is different. That's why these ones are better than that choices. That's why we're breaking this one much more than breaking that one. But still happening. You see that ones are probably secondized bit in the spectrum. So, there's a lot of questions that we ask. Given this, I could ask, what would be the responsible, what would be the fragment make this peak? Base peak is probably our most concern. But I can always question this. What would be the fragment making this peak? Then you should give me that, not this one. Right? You have to look at the structure very carefully and picking out the right one and then break it out. So that's why we still don't get any chemistry question. All right, going further. Stability of the reactive intermediates. Degree of substitutions matter. Tertiary is good, secondary is the second best. Primary is not good, but it's better than the method. But there are other factors that also stabilize reactive intermediates, like the Cadence value. What it is? Resonance structure. All right. So it sounds like an old concept we've been talking about, right? It is OChem chips. All the things OChem want basically trailing back. This molecule, almost same as what we just talked about. There's a branch right there. So, if you didn't think about anything else, what would be the base peak? Then you would probably say that I'm going to break this one, make the secondary value. That was the base peak of the previous molecule. Remember that? So if you think anything else, like a play gum, and then just answering the question, what would be the structure of the base peak? Then you will probably break it right there and then make the secondary cation right there. Because secondary cations are probably good, better than methyl cation. But there's another way, breaking out the methyl radical. I told you the methyl radical kicking out is a bad thing most of the time, but what it's left behind by kicking the methyl groups out is a cation next to the double bonds. That system. What is that system? There's some name for that. Allylic system, right? You got the allylic cation. What is special things about the allylic cation? It makes a resonance structure. The resonance stabilization is one of the key factors of stabilizing intermediates, much bigger than the degree of substitution impact. So these resonance stabilizations are something you should really count in. And I know that kicking out the methyl radical bad, but the thing is, this makes a really huge stabilization layer. So they can sacrifice kicking out the methyl radical. So if you look at that one, the fragmentation pattern, you see the methyl radical going out. That's the one makes a base peak, because that is done by the stabilization of the allylic cation produced by the methyl kicked out. Right? So the whole thing was basically nothing but most stable reactive intermediates. It's the same topic that we have talked about all the time in OChem 1. For a molecule, like an alcohol, have a different way to breaking things up. And the ethers, the nitrogens, and the chlorvinyl, now we're going to move into those type of molecules, how they got recognized. Alcohol, hydroxyl groups there, but dehydration is quick on, in the high temperature of the molecule is flying. So because of that, water can be lost. Then you got a dehydration happen during the flight. Still makes a radical cation, because we start with the radical cation, but when you do the dehydration, neutral water comes up. So still the radical cation. So dehydration peak shows up. Sometimes you don't even see these peaks at all. So that this molecular weight is supposed to be there, but nothing showing up. It's all because dehydration was so quick. So often cases you do normally consider the peaks at the highest mass is a molecular ion peak. That's what we normally conclude. Because you look at the mass spectrum and try to see which peak has the highest number, and most likely that will be responsible in matching the molecular weight. But when it becomes an alcohol, molecular ion peak may be missing because of dehydration happens so fast. So this is another layer of the thought that we need to think about as a possibility. Sometimes you use a very small molecular ion peak, sometimes it's just completely gone, but instead you get the molecular ion peak. I mean the other peak with the dehydrations. So that's a molecular weight minus 18, because the 18 is the molecular weight of the water. So that is showing up. But one thing I want to show you that is, you see these peaks are pretty tall, but this is not the base peak either. Our base peak is this one. So what is that? What makes this fragment? So those are something you should work it out by numbers. First of all, that's a 70, and then 55. If you subtract these numbers, you got 15. Whenever you see the 15s are taking out, that easily becomes like a method groups, right? Then where's the method groups coming out from that? That dehydration peak still can go to the fragmentation. That's what I have to tell you. Fragmentation can happen from here, but dehydration and that can happen from there. The method group taking out is the making of this one goes out, as we just talked about. When this one goes out, you got the cation right here. That's a allylic cation, pretty stable allylic cation. That's why this becomes the biggest peak, becomes a base peak. So in order to make it happen, you have to kick out the water, minus 18. You also have to kick out the method groups, so minus 15. The two things happen. Okay. There are something called the alpha cleavages. This one happens pretty well to alcohol, amine, ether, any of the carbonyl containing species like ketones and others. Alpha cleavages is all happening because it makes a resonance structure. You see the power of the resonance structures from the local one still applies here. Whatever the species make a resonance stabilized, the more stabilized intermediate reactive species, so it's going to stay longer, so it will be detected more well. So that's why those alpha cleavages is the biggest peak. Typically, it's one of the biggest peaks in the spectrum. So what is alpha cleavages? There's a carbon bearing the heteroatoms like oxygen, nitrogen, but we're not talking about breaking this bond. We're talking about carbon and adjacent carbon breaking right there. That is alpha cleavage. Let me show you what happens when you break this. If you break here and you give a cation this side, this carbon becomes a cation. But the thing is, this cation have an oxygen. And what oxygen is special about? It has a lone pair. What this lone pair can do, it makes a resonance structures. So that's what is alpha cleavage. It becomes one of the abundant, break the fragmentation pattern. But because it makes a resonance structures. That can happen not only with an oxygen, but also with a nitrogen. Let's say this is a carbon, another carbon there. We break this one out right there and make on this carbon carry the carbocation. That carbocation, lone pair nitrogen makes a resonance structures that makes this. So another resonance stabilized. So that makes alpha cleavage. This is ether, oxygen with the two carbon, and then we are breaking right there. That is not exactly alpha cleavages, but it actually worked the same way. What happened was, when this was broken, cation was given to the oxygens. But the thing is, when it becomes a cation, this hydride shift right over there. Hydride goes over here, make this carbon cation with oxygen there, make the resonance structures like this. So it becomes like an alpha cleavage, even though it breaks differently. What interesting was this carbonyl, when it can break right there. When it breaks right there and they give it the carbonyl, you're going to make the this carbonyl with a carbocation. That's for the acyl That looks really bad, but it is actually not as bad as you think. This lone pair of oxygen comes in, you're going to make a carbon oxygen triple bond, which is a positive charge. So that is a pretty strong fragment you're going to see. So